Swayam Prabha. Digital India. Educated India.
So this lecture is going to be interesting for you because we're going to talk about a mobile charger. All of you have a mobile charger at home. So this is the circuit that you will find inside a mobile charger where we use diodes extensively. Using this as an example, building block example, we will start analyzing various circuits using diodes. Things start getting complicated, we'll put more diodes. My job is going to be to explain it to you in the simplest fashion and understand these complex circuits. And this would pretty much cover a variety of nonlinear circuits using diodes. So we'll start with a mobile charger circuit. Mobile chargers are everywhere. You probably have maybe 3 or 4 per person in your house. If you have something that has failed, then maybe you can open it up and check it out what's inside. What you will typically see is a very standard circuit that looks like this. Okay, so first you have the input voltage which is coming in from the AC mains. And then we have a transformer that looks like this. And the transformer has a primary and the secondary is connected to secondary is a step down, of course, because at the input you have is 230 volts RMS going in 50 Hertz in India. And then the first circuit that's right after the transformer is what uses diodes, and we're going to talk about that today. The waveform which is showing up at the secondary is generally a AC waveform, and we would like to convert it to DC. So the first step would be to convert a sine wave and rectify the sine wave. Okay, so rectify, I'll explain what that means. So the first circuit that we will go through will be a rectifier. Okay, and this is where we use diodes. Output of the rectifier is generally very noisy, so we use a filter to filter out the noise, and output of the filter is then put through something called voltage regulator, and that output finally is what we see at the, let's say you have a USB port. Okay, so this is what you will see at the USB port output, and this is where you have your cell phone being charged. And output here is 5 volts, and there is some I load that's going in your cell phone battery to charge it up. Okay, let's draw some waveforms and then it will be a lot clearer. At the output, at the input is very large, 230 volts RMS, 50 Hertz. This is your AC mains. What is the reason for the transformer? First of all, let's go through that. Think about it this way. You're connecting your charger to 230 volts RMS, and output of the charger is going to your cell phone, and you're holding the cell phone in your hand. And if something goes wrong, you could get a shock. You could get electrocuted, right? One of the main jobs of the transformer, other than stepping down the voltage, is also to act as a isolation between the two sides. Okay, so there is no direct connection between your cell phone to 230 volts RMS coming in. Okay, so the output of the transformer can be something like 8 to 9 volts RMS sine wave. So this should be also like a sine wave, a smaller sine wave. And output of the rectifier would look like this. Output of the rectifier would look, so rectifier means it's like a modular circuit. So the negative part of the sine wave also gets converted to the on the positive side. Okay, and this output is then fed to the filter. So the filter will give you kind of what is the area under the curve here. It's going to filter out the high frequency noise, and it will just give you an average value. So the average value would look something like this. One thing to note here is this 230 volts RMS can change quite a lot. It can fluctuate quite a lot, which means all the way to this filter output can fluctuate quite a lot. It can be, it can go up and down by maybe plus minus 15% or so. The voltage that you want at the cell phone charging port, you want it to be pretty accurate up to 5 volts. so that you don't break down anything inside the cell phone. Okay. So you need something called a voltage regulator. What voltage regulator will do is it will convert, no matter what the input voltage is, as long as it's larger than certain value, it will convert it to 5 volts. It has something built in, a reference circuit, which will give and we call that a band gap reference, which will precisely give you 5 volts at the output. So no matter what the input voltage is fluctuating, the output of the voltage regulator will be always precise 5 volts. Let's take an example. So power transformer, this is called the power transformer here. This generally has something like 25 to 1 type of ratio. So your secondary output voltage is going to be, in this case would be, you have incoming is 230 volts multiplied by 1 divided by 25. This would be, let's say, 9.2 volts RMS. Now I'm going to go through various type of rectifier circuits using the diode. We'll start with single diode simple circuits, and then slowly we'll build complex circuits. With each example, I'll show you positives and negatives, and then we will see the improvement in the next circuit. Okay. The first circuit we are going to talk about is called half wave rectifier. As the name suggests, half wave means only half of the sinusoidal wave is used. Okay. And this circuit can be very simple. You have one diode, PN junction diode. It's connected to a resistor, and here we apply our sinusoidal AC waveform, Vin. Say plus minus like this. We can plot the transfer function as follows. We will assume a simple constant voltage model that we learned. We will say that the diode turns on at VED on voltage. So when V input is 0, at Vin equal to 0, output, the diode will be off, so the output will be equal to 0. Only when Vin goes beyond VD on, the diode will turn on. So let's say this is our VD on voltage. So till that point, this is what the diode characteristics will look like. Below this voltage also the diode is turned off. After the diode is turned on, it looks like a short according to our model, and then Vin will show up at the Vout with the subtraction of plus minus VD on. So if Vin goes up by 1 volt, then the Vout should also go up by 1 volt. So we would expect a slope of 1 right here, and that would be our Vout like this. So this would be the expected transfer characteristics. Outline a transient waveform, how that looks like, and that would be interesting. Let's draw the incoming sine wave. That would look like this, something like this. What would the output waveform look like? I want you to think about it and try to attempt it on your own before I explain the answer to you. As I said again, the diode will turn on when Vin reaches VD on. So on the y-axis, what we will do is we will draw a dotted line in red, and this is where the diode will turn on. So we expect at these points the diode will turn on. So the output characteristics, we will draw it in yellow. It should look like this. Okay. And then during this portion, the diode will be off, and again it will start when Vin reaches something like this. And this difference is right here, everywhere will be equal to VD on of the diode. So the yellow waveform is our Vout. There is another parameter that's important in the performance of a rectifier. In the previous lecture, we talked about breakdown voltage of the diode. What you can see quickly here is if you start applying larger and larger input voltage swing, then the diode will be reverse bias in this portion. Diode will be reverse biased in this portion. If the peak voltage of the input waveform is too large compared to the breakdown voltage of the diode, then the diode will break down. There is a term that is defined, it's called PIV, which is peak inverse voltage for each rectifier. and that is equal, in this case it would be equal to VA. Only half of the sine wave, that diode is in action. The rest of the half, the energy is kind of wasted. It's not turning on. Then there is the next invention, which is full wave rectifier, that we are going to talk about now. In the full wave rectifier, as the name suggests, we would like to utilize both cycles, the positive as well as negative cycle of the sine wave, to use the power from that waveform. And in this case also we have a transformer with a slight modification. In the secondary winding, we have a center tap potential. So this is reference as a ground for now, and I'm going to just draw it like this. The first half wave rectifier we can draw in this fashion. This is our load. This is identical example to what we did just now. The second half wave rectifier can be drawn in this fashion, and we will just use it in the negative part of the cycle, so that when the transformer goes on the negative side, this one kicks in, and this is your R load, and the voltage V out is across this R load. Let's call this D1, D2, and this would be your V input plus minus. What center tap does is you will get a waveform that looks like this, Vs, let's say, in the secondary, and you will have another Vs like this in the secondary. When the waveform at the top terminal of the secondary will go like this, at the same time the waveform on the other side will look like this. So let's draw the transfer characteristic. This would be your Vd on. When the diode D1 is turned on, the characteristics will look like this. And when diode D2 is turned on in the negative cycle, we would see this would be your minus Vd on, and we should see characteristics that looks like this. And here you will have a slope of -1, here you will have slope of +1. We write down here, this is when the diode D1 is on, and this is where the diode D2 is on, and D1 is off, and in this case it will be D2 is off. So when you want to analyze diode circuits, you have to initially start with a guess of which diode is turned on. Assuming that diode is turned on, you can come out with some potential numbers and things like that, and you have to verify again and make sure that the diode is actually turned on and there is current flowing through this. Let's draw transient waveform for this particular full wave rectifier, and the transient waveform will look like this. I'll draw the incoming sine wave first, something like this, and this will go on. As I said again, we will draw two lines. I'm going to exaggerate that a little bit. So in this part of the cycle, diode D1 is on, and in this part of the cycle, diode D2 is on. So we will have another threshold here, right here. So we can draw, this will be first waveform, right here. And I'm just drawing this projection to show you the time point when the diode will turn on. Since this is Vd on, and this would be minus Vd on. So the output will look like this. In this portion, the output will go to 0 because none of the diodes is turned on. So whenever you are in this range of voltage, both the diodes are turned off, and so let me write here, this is diode D1 is on. Now comes the interesting part. You just have to convince yourself again that the output will look like this. Okay, this is then diode D2 is on. The difference between these two will be Vd on. What I'm drawing here is Vs, one side of the secondary. If it's easier for you, then you can also draw this side of the secondary, which would look like this. I'm going to draw it with a different color. something like this. This would be minus Vs. This would be this waveform over here, and the yellow, the white one would be at this point. So let's call this A, let's call this B. So white one will be A and the magenta one would be the waveform B. What is the peak inverse voltage for this diode? Let's analyze that. To figure out peak inverse voltage, we should first identify the diode which is turned off. So when diode D1 is on, what's the maximum reverse bias voltage across diode D2? That's what we want to figure out, and that would be our peak inverse voltage. So in this example, let's look at diode D2 when diode D1 is at this particular point where I am showing the arrow. At that point, what would be the output? Vout will be equal to Vs minus Vd on. That would be the peak output voltage, which is shown by this yellow curve here. So that would be one terminal of this diode, and at the same time, what would be the other terminal of the diode D2? And you must have figured it out by now. That would be minus Vs, which is this particular point. So we are looking at diode D2, and quickly you can see, if I draw this particular, this would be the peak inverse voltage across the diode. That would be Vs minus Vd on minus Vs, and that value is equal to 2 Vs minus Vd on. That would be PIV. So you want this value PIV to be as small as possible. So what is the advantage and disadvantage of this one? This one, we are able to use both parts of the cycles. So diode D1 conducts during the positive cycle on the Vs, and diode D2 conducts during the negative cycle of the Vs. However, we need a special transformer which has a center tap, and we are only using half of the transformer at any point. So the next invention in full wave rectifier that will mitigate this is called bridge rectifier. In the bridge rectifier, the circuit looks as follows. I'm only going to draw the secondary part, and here we don't need a center tap transformer, so we just need a regular transformer, and this would be the output of this transformer. I would like all of you to make sure you draw these schematics in your book so that you get used to it. Unless you draw them yourself, you will not get comfortable with them, and it will also help you analyze the circuit faster. Whenever the Vs is positive, then we have two sets of diodes which are turning on. I'm going to draw them like this, okay, and then it would go through a load, it will go through another diode. Now this diode is connected differently. Pay attention. So when Vs goes positive, then we have current which is flowing something like this. So both the diodes, you can see they are turned on. Now the next part of the circuit will be flipped version of that. So this is our reference ground connection for the load RL, and here when this node goes positive or the Vs goes negative, then we want this branch to turn on, the bottom branch, called as D1, D2, D3 and D4. So during positive cycle of Vs, what is going to happen? The current will flow like this. And the voltage will be plus minus, plus minus, plus minus. So here you can see what's the output potential is going to be. Vs minus 2 Vd on. That would be your voltage across the load, V out. Similarly, you can convince yourself now that in the negative cycle of Vs, positive cycle of Vs, we had diodes D2 and D4 were on, and V out was equal to Vs minus 2 times Vd on. In the negative cycle of Vs, we will have this node getting positive compared to the top, and the diode D3 will turn on, and then we will go through the load resistor, and then diode D1 will turn on, and that's the way we will complete our circuit. So in this case, you will have plus minus, diode D1 will be turned on, Vd on, plus minus, that will be your V out, and then plus minus will be Vd on across diode D1, and you would again get V out is equal to Vs minus 2 Vd on. That would be the peak voltage at the output. What's the difference here? The peak inverse voltage, let's see how much that comes out to be for this case. To understand the peak inverse case, I'm going to redraw it a little bit, or maybe we can just redraw it here. So let's consider the case when diodes D2 and D4 are on. In that case, the voltage, what would be the voltage V0? That would be equal to V out is equal to Vs minus 2 Vd on, because there is plus minus Vd on here, and there is also plus minus Vd on across these guys, and this would be our, this is equal to plus minus Vs. Now we will figure out what is the reverse bias voltage for diodes D1 and D3. Let's take an example of the diode D3. So reverse bias voltage across D3. You can quickly see the potential at this node is minus Vd on, and the potential at this node is Vs minus 2 Vd on. So the peak inverse voltage will be Vs minus 2 Vd on minus Vd on. This is our PIV, and this is equal to Vs minus Vd on. So you can see peak inverse voltage is smaller, so these diodes don't have to handle larger peak inverse voltage. So that's the advantage of this particular topology compared to the previous one. In the previous one, if you remember, it was 2 times Vs minus Vd on. In this case, it's only Vs minus Vd on. Let me remind you again. So let's go over, take a look. In the previous case, in the previous full wave rectifier, we said, yeah, the peak inverse voltage we had calculated was 2 times Vs minus Vd on. So each diode faces 2x the input voltage as an inverse voltage, reverse bias voltage. So these diodes need to be able to withstand larger reverse bias voltage compared to bridge rectifier, where we see it's only single Vs here minus Vd on. So what are the advantages of this particular bridge rectifier? First of all, we don't need a center tap transformer. We don't need that. So that's a positive thing. Of course, we need 4 diodes, but diodes are cheap, so it's okay. And at a time, only 2 diodes are on, and they are in series, and that gives you your peak output voltage will be Vs minus 2 Vd on, and PIV is Vs minus Vd on. So this is a positive, smaller. And another difference is half the number of turns required for the transformer, And this is a most popular rectifier design. It's everywhere. It's ubiquitous. You will see it in so many applications because of its advantages. We will move on to the next block in our charger circuit. Let's draw so here is our rectifier, something like this. So I'm just putting it in a box as whatever choice of rectifier we use. At the output of the rectifier, we have this waveform which is going in only in one direction. So it could be either like this, or it could be something like this. This is your half wave and this is your full wave. So this by itself is so noisy that we cannot directly use it. So what we do then is we put a filter at its output. The filter can be as simple as just a simple capacitor, and this would be your iLoad, which could be your phone or any other device you are trying to charge, and this would be V0 output. Let's see how this works. So if you have a rectified waveform which looks like this, and we put a capacitor in front of it, then what we expect to see is something very simple. The capacitor will get charged, and once the capacitor is charged, it will hold its value, and the output will stay like this. This is true when iLoad is 0. There is no current drawn, and since the capacitor never gets discharged, it will just hold the output value, voltage V0. That would be like here. However, if you draw some current to charge your device, then in this portion right here, you will start losing some of the charge, and it will start going down like this. It will start getting discharged, and again it comes back in the next cycle, it gets charged, and then it discharges again, starts getting charged, something like this. So at the output waveform with the capacitor, the magenta waveform was V0 under no load. The green waveform is showing V0 with load because we are withdrawing some charges from the capacitor in terms of iLoad. Let's go through a numerical example. So we are doing full wave rectifier, and we would like to deliver 1 watt of power to your mobile phone. So this 1 watt number is important in the design of your charger. If you take your charger and maybe use a magnifying glass, at the bottom of the charger you will see few numbers. One of the numbers will say 100 volts to 230 volts. What that means is this charger can be used anywhere worldwide. It can be used in United States, it can be used in India, it can be used in any other country, because generally the AC voltage ranges from 100 volts all the way to maximum 230 or 250 volts. The next number, important number that you will see on the charger is wattage. The output voltage is going to be 5 volts, and it can deliver so many watts to the load. Now that's an important number because with advances in the cell phone technology and the battery technology, the charger ratings have gone up substantially. And nowadays we are not at all patient with getting your phones charged. We would like them to be charged quickly. The charger has to provide lot higher power, and typical numbers you will see something like a 12 watt or 15 watt, something like that. Okay. Now coming back to our example, we would like to deliver 1 watt to mobile phone with V0 is equal to 5 volts. And important specification is the V ripple, this needs to be maximum 0.25 volts. The ripple voltage, I'm going to show you what that looks like. It's this voltage, which is the V ripple. So for this condition, what's the minimum value of C we need to use? Capacitance we need to use. We will make simplistic assumptions so that we can quickly calculate the numbers and get an idea of the numbers. From this information, how do we backtrack and come back with an approximate value of the C? That's what we're going to go through in this example. Okay. So first of all, let's draw the waveform. The waveform is going to look like this. There will be some dead zone, after which it will again go like this, and there will be small dead zone. It will go like this. With the capacitor there, we expect the waveform to look from this peak value. It will drop a little bit, it will charge again, drop a little bit, and then it will charge again, and it will keep going. We would like to make sure that this value is the V ripple, that should be 0.25 volts maximum with the capacitor. Now what else do we know? We know that since it's a full wave rectifier, this period is equal to T divided by 2. This period is equal to T divided by 2. So here we know the final output voltage V0 is equal to 5 volt. So we have to backtrack from this information our peak voltage, and for full wave rectifier we know that V0 peak is equal to V in peak minus 2 times Vd on. Now we know V0 peak, we want it to be 5 volts. So V in peak will be equal to V0 peak plus 2 Vd on. Let's substitute values. This is 5 volts plus 2 times, let's assume Vd on to be equal to 0.8 volts. So this is going to look like 6.6 volts peak. What this is telling you is the transformer is going to step down from 230 volts RMS multiplied by root 2 volts peak, okay, to about 6.6 volts peak. That would be the transformer turns ratio. And all this stuff is happening at 50 Hertz. Now let's only look at this portion of the curve magnified and try to understand what's really going on. So the ripple is going to look like this. This distance is T divided by 2. We are going to assume that the ripple is small. So we are going to assume and we are going to ignore this portion of the curve where the capacitor is getting charged. Since we assume the vertical ripple is, I have exaggerated it a little bit here. V ripple is small, and you can see it's 250 millivolts as compared to 5 volts. So ripple value is small, and we are going to say that, hey, let's ignore this portion of the curve for now. So we get an equation, dV out by dt is equal to I load divided by the capacitor C. Just for your understanding, we are only looking at model that looks as simplistic as this. So this is your I load and this is the capacitor C, and this curve is going to give us dV out by dt. So we are going to say dV out, with all the approximations we have made, dV out is equal to V ripple. What is dt? dt is the time period, which is T divided by 2, and that is given by I load divided by C. So this equation will give us C is equal to I load divided by 2 times V ripple times reciprocal of T would be the frequency. Now what is I load? I load is given by, we were given power information, power divided by the V peak voltage. So we can say C is equal to power divided by V out peak and then divided by 2 V ripple and then frequency. So power, let's substitute the values. Power is 1 watt divided by, we wanted 5 volts peak multiplied by 2, the V ripple is equal to 0.25 volts multiplied by 50 hertz. So the capacitor value is, if you calculate, you will see this is equal to 1 watt, 1 divided by, so this should be 1 watt divided by 125 and that would be equal to 8 millifarads. Now this capacitance value looks like it's pretty large, but you get the idea how to go about doing the computation. If you look at diode based circuit, then we have already seen that we need about 750 millivolts or 800 millivolts to turn on the diodes, D on. So that by itself suggests that we need to have input voltages which are larger than that, AC input voltages which are larger than that, so that we can rectify. But there are many circuit applications, and one of them I'm going to show it to you, where the input voltages are very small. It can be millivolts, it can be tens or hundreds of millivolts. Then how do you rectify those signals? And one good example of that, which all of us use in our cell phones, is something called received signal strength indicator. Okay, so this is a little bit of a detour, but you will appreciate what this circuit does for you. When you're receiving signal on your cell phone, one of the most important thing you have to watch out for is make sure that you provide enough gain, because the signals which you are receiving are weak. So you would like to amplify them. However, you don't want to amplify them too much, because if you amplify them too much, then you will clip them. And if you clip them, then you will lose information. So you need a circuit which will tell you the magnitude or the power level of the incoming signal, received signal. So for which we need a rectification. Even though the waveform is really small, it can be microvolts, millivolts, you need to somehow be able to do the, for example, if this is the waveform, then I would draw it in this way and you get the point. So this would be a rectified waveform, even though it's something like that. So this would be your rectified small signal voltage, and this could be in millivolts. So the challenge is, how do you do that without amplifying it? And the limitation we have is, as I said, VD on is equal to 750 to 800 millivolts. So we will use our new friend called op-amp and see if we can design a circuit that would do the job for you. At the output of the op-amp, I'm going to connect a diode like this. And this is where my RL load is. And this would be our Vout. So first important thing is, what would be the signs at the input of the op-amp? We should be able to tell that this op-amp should be in negative feedback mode, and for that the diode needs to be on for the negative feedback mode. So the diode D1 is on, and if the diode D1 is on, then this terminal needs to be negative, this terminal needs to be positive. Now let's analyze this particular circuit. What's the transfer characteristics going to look like? This is my V in and this is V out. So let's assume that diode D1 is on and the feedback is on. So if the feedback is on, then V in, voltage V in should show up because of the virtual short. This should be also V in. If the diode D1 is on, then we should see plus minus VD on. Diode D1 is on, and this voltage should be Vin plus VD on. So this seems reasonable. Now the Vin shows up at the Vout. The output looks like straight away from here, just like this. And you will have slope of 1. This is Vin. What happens when Vin is less than 0? So let me write it down first. When Vin is greater than 0, then D1 is on and feedback is on, is working. V op amp is equal to, this is V op amp, that will be equal to V0 plus VB on. And of course, most important output V0 is equal to Vn. The key observation here is that it doesn't matter what value of Vn is. The Vn can be less than Vd on, this will still work. So the limitation of the diode, 750, 800 millivolts to turn it on, doesn't really bother us. When Vin is less than 0, then what happens? What we would expect is, if Vin is less than 0, you can analyze it. The diode D1 will be off, and if the diode D1 is off, then we don't care what's at the output of the op amp. The feedback is broken. Probably it will be negative voltage there at the output of the op amp. That will satisfy our D1 is off case. Vout will be equal to 0 because there is no current flowing through RL. So we can draw the rest of the characteristics. Looks like this for Vin less than 0. So the key point is, without op amp, you can only rectify signals which are greater than VD on or 0.7, 0.75 volts or so. But with op amp, we can overcome this limitation. And this circuit is also commonly used many times to do small signal rectification. Next circuit we are going to go through is called limiting or clamping. Let me draw the circuit for you and then explain it to you what it does. So I have chosen, handpicked a few circuits so that once you get exposed to them, you can easily do more complex circuits. So what's really going on here is the following. This is diode D1 and this is diode D2, and the voltage is, output voltage is across V0 here. Again, we draw the transfer characteristics. So Vin equal to 0, what do we expect? Diode D1 and D2 both will be off. So output will look like Vn. When does diode D2 turn on? The diode D2 will turn on when Vn is greater than Vd on. So we will draw 2 points here and corresponding 2 points here. So during this range, when Vn is when Vn is greater than, this is Vn and this is Vout. When Vn is greater than Vd on, then we expect the output, the diode D2 will be turned on. So the output will be flat at Vd on. Before that, we expect both D1 and D2 are off. If D1 and D2 are off, then V0 is equal to Vn. So the transfer curve looks like this. So this would be D2 is on in this region. And you can analyze the rest of it, which is exactly flipped, so that the curve should look like this. So in this portion, D1 is on, and in between, both D1 and D2 are off. So the key point here is, both D1 and D2 are off, then Vout is equal to Vn. And as soon as Vn increases beyond plus Vd on or minus Vd on, then the diodes are on and your output, here we call it, it's clamped or limited. It doesn't grow beyond that. Okay. So this circuit is used in many places where you would like to limit the voltage being fed into your circuits. You don't want them to grow beyond certain value because it will damage something in your circuit. One good example of that would be ESD protection, electrostatic discharge. So you're protecting your integrated circuits from large voltages. In that case, you use circuits similar to this to protect your sensitive circuits inside from static discharge from your body. The next circuit we are going to use Zener diodes. We'll go through one example of a Zener diode, so you're also familiar with using them. A Zener diode is drawn this way, and when the Zener diode is reverse biased, you should see plus minus Vz across it during reverse bias, and forward biased you will see plus minus Vd on, the diode on voltage. Okay, so let's draw the schematic and try to understand what's going on. So here I have a resistor and I'm going to put two Zener diodes back to back this way, and the other one is, let's apply voltage V in. Again here we will try to figure out what the output voltage VO is and the transfer. So here we will again draw V in and V out. So when V in equal to 0, both diodes Z1 and Z2 both will be off. They are neither in reverse bias or on case. Okay, so we should see if both diodes don't exist, then V out is equal to V in. So you know this part of the curve right there. And as you start increasing your V in voltage, what will happen? You will start, the diode Z1 will start turning on because you're taking its anode positive, and diode Z2 will get reverse biased. Both diodes will turn on when this is Vd on and plus minus you have Vz. So you can see that output is equal to input till the voltage reached is Vz2 plus Vd on 1. So till that point output is equal to input, you should get a slope of 1. Curve that looks like this, and beyond that Vz is also in reverse bias and Vd on of course is turned on. So the output voltage, we will see it stay flat and the current will keep increasing, and the value of the current in this circuit will be equal to V in minus Vd on plus Vd on 1 and Vz2 divided by R. That will be the I. That will be the I in flowing. Okay. Similarly, when you go to the other side, you can convince yourself that it should be here this way. Vz1 plus Vd on 2 negative sign. And it will get limited here. So this circuit is a limiter circuit using a Zener diode. Thank you.